Ready as I'll ever be. Good afternoon. I hope everybody can hear okay. Just if you could just notify us if you can hear. We're just making sure that everybody can hear when we start. Anything? Okay, I'm just going to assume that everybody can hear. So good afternoon and welcome to this Angstrom Technology webinar, which is intended to give you an overview of cleanroom validations to ISO 14644 Part 1, but also EU GMP standards and the supporting tests. Thank you all for joining and appreciate you all have busy schedules. Hopefully you can gain something from this half an hour and take some value away from it.
We're coming to you live from the Angstrom Technology UK head office in Lancaster. The webinar is also being recorded and will be shared to all current viewers and also available on our YouTube channel and our own website later.
Okay, so this is our first validation webinar, hopefully in a series, and today we're going to be going through who we are as a company, what is a clean room, what is cleanroom qualification and why it is important, the importance of maintenance and calibrations, ISO 14644 Parts 1 and 3, 2015 and 2019, the importance of accurate reporting. We will then open the floor to your questions if you have any. I'm sure that you will. All we ask is that you please raise them in the chat box and we'll try and cover as many as we can at the end. So, to introduce myself, I'm Mark Jackson, Commissioning and Validation Manager for Angstrom Technology. I've been with the business for over 20 years and have experience in cleanroom design, build, commissioning, validation and ongoing maintenance. I also get involved with providing advice and clean solutions for customers with contamination issues and can provide a methodical approach to deliver tailored solutions.
Hi, I'm Nick Rhodes, Commissioning and Validation Lead, and I have over 20 years experience in ventilation, balancing, commissioning and validating both centralized and decentralized air handling systems for NHS facilities, universities, hotels, operating theatres, clean rooms, microbiological safety cabinets and isolators, LEV systems. Pretty much, if it has a fan, it moves air, I will work on it.
The list is endless, mate. The list is endless.
Angstrom Technology, part of the Angstrom Group, and our offices based in the USA and UK, delivering over 6,000 clean rooms to customers worldwide. At Angstrom, we are specialists who support the full clean room life cycle, design and build, validation and requalification, GMP consultancy, consumables and equipment, clean room training, and particle counter calibrations.
So today's webinar is intended to convey to you the importance of periodic cleanroom qualification and what is involved in the testing of a clean room. Before we get into the cleanroom validation and the processes involved, I think it is important to define exactly what a clean room is for those that are new to cleanroom environments. So a clean room is a room within which the concentration of airborne particles is controlled and which is constructed and used in a manner to minimize the introduction, generation and retention of particles inside the room. Other relevant parameters such as temperature, humidity and pressure are also controlled as necessary. Clean rooms are classified into different classes depending on the number of particles allowed in the air per cubic meter, and two standards are generally used to classify them, those being ISO 14644 Part 1 2015 and the EU GMP standard.
Qualification of a clean room is a similar process to getting your car MOT'd. The tests involved are designed to ensure that the clean room is operating correctly and to the standards they are designed to. The tests involved are designed to ensure the facility is operating at the levels of cleanliness required by the owners, their customers, and perhaps external regulatory bodies. By successfully completing these tests, you can increase the sterility of pharmaceutical products, prevent damage to other equipment in the cleanroom environment due to exposure to particles, And of course, a reliable test method reduces contamination levels of finished products as well. Regular cleanroom qualification helps to detect and identify the source of any harmful contaminants, gives assurance to regulatory bodies such as ISO or EU GMP, as previously mentioned, so that the cleanroom meets its desired classification. And it also reduces operational downtime and maintenance costs, as the majority of the works are pre-planned and budgeted for. ISO 14644 Part 2 of 2015, which is monitoring to provide evidence of cleanroom performance related to air cleanliness by particle concentration, recommends customers to complete risk assessments and monitoring plans to determine the frequency of testing and validation for their individual processes. It states that the suggested maximum time interval between airborne particle counting of a cleanroom of ISO class 5 and below is 6 months, and ISO class 6 and above is 12 months. However, this should be assessed to ensure it is in line with your own monitoring plan and risk assessment, which is required to be reviewed on a regular basis.
Okay, so good manufacturing practice, EU GMP, describes a minimum standard a medicines manufacturer must meet in their production processes. EU GMP Annex 1 details a maximum permitted particle concentrations for classification for at-rest and in-operation states for sterile manufacturers. The maximum time interval for requalification of grade A and B areas is 6 months and 12 months for grade C and D areas. This slide just highlights the difference between the ISO and the EU GMP. So the ISO class stays the same for ISO status in operation, at rest and as built, but in GMP, class limits decrease for operational status of the room. For example, grade B reduces from ISO class 5 to class 7, grade C reduces from ISO class 7 to class 8, and grade D reduces from ISO class 8 to unclassified. All reduce with the exception of grade A, which remains the same ISO class 5 in both statuses. So before we even discuss the actual validation methods of a clean room, there are two other important areas to consider. Firstly, if you are having an engineer come to your facility for testing, let's be honest, the only thing that concerns you as production manager or quality assurance team is that pass or fail comment at the bottom of your report. There are pre-planned courses of maintenance that you can undertake to ensure this runs as smoothly as possible. If it's an AHU system, check the belt alignment, belt tensions, change panel and bag filters, check your AHU frequencies are all very similar to the last visit recorded. For an AC unit on the system, regular servicing and cleaning of coils, and of course, regular cleaning and maintenance inside the actual clean room. All of this can be the difference between a pass and a fail. Nobody wants to fail because this causes downtime in production. Secondly, calibration of equipment. This not only covers the sensors you may have within your facility, such as airflow and pressure sensors, but more importantly, this is for the validation engineer's equipment. All the kit used by an engineer should be in good working order and calibrated because it helps ensure accurate, repeatable measurements. These are the foundation of the quality, safety, and innovation of most products and services we use and rely on every day.
So let's get into it. How do you qualify a clean room? There is simply one test covered by ISO 14644 Part 1 of 2015, which is the classification of air cleanliness by particle concentration, or quite simply put, particle counting. All of the remaining tests covered in ISO 14644 Part 3 of 2019 are supporting tests only, which are appropriate for measuring the performance of a clean room. And these supporting tests and their frequency should be agreed with the client beforehand. Dependent on the design specification and URS created by the client, this will determine which additional supporting tests are required when requalifying the facility. Temperature and humidity ranges, rim differential pressures, lux levels are examples of these, and the pass-fail criteria will be determined by the specifications in the URS.
To perform particle counting, we would use a light scattering airborne particle counter, or LSAPC for short, usually a handheld or a portable, as per the two devices shown on screen. These devices would be attached to an isokinetic probe with some sampling tube. A tripod may be used for support. So the isokinetic probe is determined by the particle counter's flow rate, and the sampling tube should be kept to a minimum length. The particle counter must be capable of measuring the particle sizes you are wanting to consider, and must also be able to measure more particles than the maximum limit of the class.
What you can see here is the table within the ISO 14644 Part 1 standard, which illustrates the number of particle counting locations in relation to the area of the room. The engineer will measure the room area, and using the table A.1 will look up the number of locations required to sample. For example, a room with an area of 10 meters squared would require 5 locations. A room 15 meters squared is situated between the 10 and 24 meter squared boundaries, and therefore the engineer should select the higher amount of locations, in this example 6 locations. The sample time for each location is determined by the ISO class the room is designed to and the largest particle size tested. A lot of the current particle counters sold today have this information pre-programmed into them, and if they are set up correctly by the engineer, can efficiently display the required information to the user.
After the particle count samples are taken, the engineer will refer to Table 1 ISO class of air cleanliness by particle concentration. This table contains the maximum allowable concentrations of particle sizes by the ISO class. Most engineers have these levels committed to memory, but just in case they don't, it's here to refer to. The engineer will now be able to determine what ISO classification the cleanroom has achieved. For reporting purposes, this will have to include the ISO class, the occupancy state, and the lower and upper considered particle sizes. For example, an ISO class 7 cleanroom must have less than 352,000 particles at 0.5 micron and less than 2,930 particles at 5 micron in each location sampled. The average count for the room may pass, but should any one location exceed the allowable concentration, that will cause the room to fail.
So the clean room can be defined as follows. The ISO class we are qualifying the room to, the 3 occupancy states, which are as built, at rest, and operational. As built, the clean room has never been used. It is brand new and probably the cleanest it will ever be. At rest, people have used the clean room and completed intended works, but they are not present in the rooms during testing taking place. It is not as clean as brand new, but it is cleaner than when the room is occupied with people moving around. This is often a measurement used to make sure ventilation systems and filters are working properly. It is what the room is capable of achieving now that you have been using it. Finally, operational. This means that you are measuring the air quality during the normal course of the day whilst the room is occupied, with people doing things and moving around. This is usually the dirtiest time since people provide most of the airborne particulate and stir up particulate from surfaces. The lower and upper considered particle sizes from the table 1 above, you can see that the particle size is usually considered a 0.1, 0.2, 0.3, 0.5, 1 and 5 microns, with the most popular being the 0.3, 0.5 and 5 micron sizes. So a typical clean room classification, as shown on the screen, could be stated as ISO class 6, operational, 0.3 microns, 5 microns.
So all of the remaining testing procedures are contained within ISO 14644 Part 3, test methods. They are all supporting tests which are appropriate for measuring the performance status of the clean room. These include airflows, air change rates, pressure differentials, filter integrity testing, airflow visualization, recovery rate, containment, temperature and humidity and lux levels, and electrostatic testing. These additional tests provide evidence which would support that the operation of the clean rooms and zones are able to meet their air cleanliness classification, other cleanliness attributes, and related controlled conditions. Air change rates would normally require velocities to be taken using an anemometer or volumes using a bolometer and then calculated. Pressure differentials are usually taken on the door thresholds using a manometer. Filter integrity will require a contaminant being introduced before the filter upstream, usually by a smoke generator, and then the filter, frame, and housing is scanned using a photometer downstream. Airflow visualization requires smoke being released within the suite and is filmed to visualize the airflow patterns. Recovery rates, again, require smoke being released within the suite, and a particle counter is used to determine how quickly the counts return to normal within the permissible range. Containment testing also requires the use of a smoke generator, and dependent on whether the room is positively or negatively pressured, will determine where the smoke is released. The leaks are then detected using either a particle counter or photometer. Temperature, humidity, lux, and electrostatic testing will all require various specific instruments to complete the tests.
Reporting is also an essential part of the process. Everyone wants to see the word pass all over their final report, but these reports should also highlight any failures or non-conformities so that corrective actions may be taken, and the facility can then be fully retested, ensuring a high level of conformity to the standards being used. In the event of any failures being found at the testing stage, it will be recommended that all production should cease, and any corrective actions should be completed before normal production resumes. It is also recommended that the estates or maintenance team within the client's facility hold critical spare parts so that the downtime is reduced to a minimum. At Angstrom Technology, for some clients that have already acquired their specific critical spares, we will hold them within our warehouse area, and these are brought to site when the qualification takes place for a time-sensitive replacement. Occasionally, requalification failure can be down to operational malpractice, such as incorrect gowning, contaminants being brought into the clean room by the users, and not following standard operating procedures defined by the client. Upon rectifying these issues by retraining or re-educating users, this may considerably reduce the contaminants, and the clean room may then pass the testing.
So we hope that you've enjoyed our extremely brief insight into the validation of clean rooms. We are hoping to produce more similar webinars in the future, which will go into more detail into the actual tests performed and how to perform them, as well as providing a structured cleanroom testing course later next year. If your company requires more detailed training on any aspect of cleanroom validations, the different standards used such as EU GMP or cleanroom etiquette, then please contact us directly and we will be happy to provide you with more information.
We're now going to open up to any questions from anybody viewing. So let's see what people have asked. The question that I can first see, which is from Tyler, is what is MOT, which we mentioned quite early on. This is actually for a motor vehicle in the UK, and every 12 months your car has to be inspected to make sure that it's suitable to be able to be driven on UK roads. And this obviously is comparable to having a clean room validation, which is again every 12-month period. We also have some questions which have been sent in when the webinar went live for registration, and because we've got time now, we're going to analyze them in a bit more detail.
Okay, so one question that was asked was, I have an ISO class 7 soft wall clean room measuring 30 meters squared. How long would it take to validate? So it's a rather open-ended question, a bit like how long is a piece of string. It all depends on whether it's an annual validation or just an interim validation check. The assumption from our knowledge of clean rooms is that the size of the room for an ISO class 7 would probably have between 2 and 4 filters. From that, we would say that an annual validation would probably take between 2 and 3 hours, and an interim can be reduced down in time as there's no filter integrity testing to be done. We would only normally test the new filters at the installation stage, so the interim wouldn't require that test. So the amount of testing done would be reduced down. So it depends. So there's a lot more questions we need to answer, really, that we need to ask the customer who's asked that question. Maybe we need to get up-to-date drawings of that clean room as well, just to make sure that we can answer more definitively. Another question that we've been asked. So I think it's come up on the screen. What is the most common issues that companies face during validations? Obviously, the most common one is quite simply it's failed on particle counts. As we covered earlier in this webinar, this could be down to maintenance issues or lack of training of employees. The engineer on site should indicate to the customer whether this is a mechanical failure, such as maybe fans or HEPA filters failing. But they may also include if it's down to user practice, and that potentially these are adding to the types of failure. Maybe it could be users. We would say pre-planned maintenance and user training can and will reduce all these issues. So hopefully that answers that question. Another question that we've had, sorry, Nick, do you want to answer this one?
Can do, Mark, not a problem. How can I consider the costs of validating my clean room against the potential risks of non-compliance? This is actually an excellent and practical question, especially for those industries with budget constraints. You've got to weigh up the risk management versus the cost. We need to acknowledge that sometimes difficult balancing act that companies face when trying to invest in achieving compliance versus the potentially unforeseen consequences of non-compliance, such as contamination of products, costly recalls of those products, or regulatory sanctions to enforce future compliance. We could open up a long and drawn-out debate on cost savings. What we would suggest is that the company looks for cost-saving efficiencies while also maintaining its standards. Sometimes an external company providing a site survey can highlight these potential savings to your company and will consider things that you cannot see as you are too close to the action. My final comment will be that although there are costs incurred, this is counteracted by the fact that there is a lot of value to be added when compliance is achieved and maintained.
Thank you, Nick. I'm just looking in the chat box, and it doesn't look like there's any more questions that have been added. So if there's anything that anybody would like to add just before we close up, please do so now. If not, we'll probably wrap up. Obviously, if my final parting comments before we close the webinar is thank you all very much for joining. If you have any further questions to ask, please send them through to the email addresses shown on the screen: mark.jackson@angstromtech.com and nick.rhodes@angstromtech.com. We are happy to answer them. If you send them through, we'll answer them as quickly as possible. But if there's nothing else to answer in the chat box, we'll say thank you and goodbye.
Thank you for sending.
Thank you.